Hello everybody, this is Dr. Christopher White, and today we are going to be looking at sedimentary environments and rocks. So what are our objectives? Well, first of all, we're going to think, how do sedimentary rocks form? What are the different types of sedimentary rocks? What are the different layers and features of sedimentary rocks, so sedimentary structures, and how do they form? What are the environments in which sedimentary rocks form? And how do we study rocks, infer environments, and reconstruct changes in those environments, that occurred in the area, using sedimentary rocks? So this is a diagram we're all very familiar with by now. This is our rock cycle diagram, and the sedimentary portion, as I'm sure you know, is up here in the top, marked out by this lovely red box. So in terms of the sedimentary cycle, obviously it begins with weathering, so we take a pre-existing rock that's exposed to the atmosphere, and the action of several chemical reactions, which we'll be discussing in a few slides' time, cause that rock to become weak, and it begins to fall to pieces. Those pieces of rock will be transported. Now remember, transportation can occur by one of four mediums: water, wind, ice, or gravity. The most common one is water, but the other three are also possibilities. So the sediment that was produced by weathering will be transported, and during the transportation process it will be eroded, and the size and shape of the pieces of rock will change as the sediment is transported along. Eventually we get to the situation where the sediment is deposited, and when the sediment is deposited, it will typically be deposited as horizontal sheets. So you'll get a layer of sediment that's deposited. Now, as I'm sure you guys can work out for yourselves, over time that means we're going to get layer after layer after layer of sediment building up in an area. So just in front of this delta here, we're going to have layer after layer after layer of sediment. You can see them down here on the side of the diagram there. Now this means that layers which are initially at the top of the stack, like this cream coloured layer here, will steadily have more and more material deposited on top of them, and so they will steadily get pushed deeper and deeper into the stack, into the sequence. Now as this happens, obviously that means they are being buried, and during the process of being buried they will begin to be exposed to increased pressure and increased temperature, and this will eventually lead to the process of lithification, and this is the process by which we are taking our sediment and turning it into a proper rock. Now obviously you can see the paragraph down here. We're actually going to cover lithification in much greater detail in a few slides' time, so I'm really not going to spend any time on that right now. Okay, so sedimentary environments. So the thing we need to remember is that each environment contains unique processes that will form a specific type of rock and produce distinguishing features among the layers as it becomes lithified. So as you can see on this diagram, we have several different environments. We've got aeolian environments, so desert environments essentially. We have alluvial fans. They occur along the high ground, along the margins of desert basins. We have player lake environments. Those are short-term bodies of water that typically evaporate away in desert environments. We have glacial environments, fluvial or river environments, beach environments, deltas, tidal flats, barrier islands, the shelf environment. That's the relatively shallow water just off the coast here, typically between about 0 and 200 meters deep. We have organic reefs, or otherwise known as coral reefs. We have the continental slope here. At the bottom of the continental slope we have submarine fans forming. They are produced by mass flows or landslides of material as it comes pouring off the shelf and comes down the continental slope, and eventually those fans will come to rest in this environment down here, which we refer to as the deep marine, also sometimes referred to as the abyssal plain. Now each of these different environments have different conditions, and that will mean that certain types of rock will be more likely to form in these different environments. So for instance, in a organic reef or coral reef, well, we would obviously expect to find rocks like limestone, and we would expect those limestones to have very large quantities of fossils in them, particularly coral fossils. We would not expect to find a limestone with lots of coral fossils forming in a desert environment, however. We would expect to find a sandstone forming in that desert environment. And that sandstone would probably have what we refer to as crossbeds in it, which is a crossbed is a type of structure, which once again we will be discussing a lot more in the next lecture. Now, the most important thing about sedimentary environments is they are split into three very broad groups. There are the continental sedimentary environments, and shock horror, those are the ones that occur on land. So that's environments like the Aeolian environment, alluvial fans, playa lakes, glaciers, fluvial environments. So please note that fluvial environments are freshwater environments, and they are considered to be continental because they are occurring on land. The next group of environments we have are the transitional environments. So the transitional environments are environments which spend a portion of their time above sea level and a portion of their time below sea level. So those are going to be environments like lagoons, barrier islands like this linear feature here, beaches, deltas, tidal flats. The final group is a group of environments that occur exclusively in settings which are 100% under salt water, so completely marine the entire time. And these are obviously going to be referred to as the marine environments, and those are going to be environments like the continental shelf, organic reefs, the continental slope, submarine fans, and deep marine environment, also called the abyssal plain. So these individual environments are split into three broad groups: continental, transitional, and marine. I should also point out that transition is also sometimes referred to as intermediate, so please excuse me if I happen to flip between the terms. Alright, so what are we looking at in this lecture? Well, first of all, we're going to think about sedimentary processes, so the weathering, transportation, deposition, compaction, cementation, and recrystallization of sediments to actually make a rock. We're also going to think about the types of sedimentary rocks that are formed. So we're going to think about clastic sedimentary rocks and non-clastic sedimentary rocks. And you're going to see that, normally when we think about sedimentary rocks, we think of the obvious ones. We think of a rock like sandstone. Well, that's a clastic rock. So obviously that's made of bits of other rocks and minerals. And you can feel it when you touch a sandstone. It feels gritty. It feels like sandpaper because it's made of lots of pieces of other rocks and minerals. However, there is also another class of rock which is called non-clastic sedimentary rocks, and those are typically produced by organic and inorganic processes. So that can be things like limestones. Limestones are typically produced by organic material, shell material, or coal. Coal is the result of essentially undecomposed organic material, bits of plant that never rotted. You also can have inorganic non-clastic sedimentary rocks, and those would be things like halite or rock salt. Well, that's produced by the evaporation of large quantities of water. In all those situations, there are no clasts involved, so there are no bits of rocks and minerals involved in the process. So, why are sedimentary rocks important? Well, sedimentary rocks are important because they actually have quite a large economic impact. So, sedimentary rocks are where we find the coal seams. They're where we find the oil and natural gas. They are where we find the vast majority of mineable iron, mineable aluminum, and mineable manganese, to mention but a few. So they have a very, very important economic significance. I should point out, by the way, that at the moment coal is steadily becoming less and less popular. We are going to discuss it, but it's worth pointing out that coal is on its way out as a resource now. Sedimentary rocks, however, from a purely geologic point of view, are of greatest importance to us because they provide evidence of past environments and may also contain fossils. So the thing about a sedimentary rock is, a sedimentary rock is the only type of rock that actually tells us or shows us what was going on the surface of the earth. So think about it, a metamorphic rock, well, they form underground. They aren't going to tell us anything about what was happening on the surface of the earth. An igneous rock, well, an igneous rock can tell us a little bit about what's happening on the surface of the earth. Volcanic igneous rocks can tell us, right, was this lava erupted underwater? Or was this lava erupted onto dry land? Now that's helpful. It can tell you were you underwater or were you on dry land. But apart from that, it doesn't really tell you that much. So on the whole, metamorphic and igneous rocks are pretty much useless when it comes to telling us what the conditions on the surface of the Earth at a given location at a given time were. However, sedimentary rocks can do that for us. We can look at a sedimentary rock and we can say, right, based on what we're seeing in this sedimentary rock, I know that this location where I'm standing right now during the Permian was a, for instance, swamp. And if you know it's a swamp environment, well, obviously you can make some assumptions about the type of conditions that you probably were standing in. You know, it's probably quite hot and probably quite humid, and you're probably somewhere near a coastline. And you can then probably assume with relative certainty that because you're in these hot, humid conditions, you are probably, you know, somewhere nearer the equator than you are towards the North or South Pole. So you can read quite a lot into, you know, the environment and what was going on based on the types of sedimentary rocks that you have in an area. So in terms of the resources in sedimentary rocks, why are they important? Well, sedimentary rocks, I'm just going to skip to all these. Sedimentary rocks are, on the whole, the classic ones especially, are porous. That means they have voids inside them. And those voids can fill up with stuff. Those voids can fill up with groundwater. They can fill up with oil and gas. And sometimes when the groundwaters move through these very porous and permeable layers of sedimentary rock, they can deposit minerals as they go. So for instance, one of the sources of uranium is a type of deposit called a roll front uranium deposit. And that's produced as groundwaters move along a permeable layer, and as they're moving along, they end up depositing uranium in one spot as they go, and later on we come along and we dig up that rock containing the uranium and we extract it for use in nuclear reactors. So the permeable nature of sedimentary rocks is quite important to us. Sedimentary rocks, as I mentioned, are also the only type of rock in which we find coal. Now, coal in the past was a very, very important rock. It's becoming less and less important now. Sedimentary rocks are also used for cement. If you've ever worked on any kind of construction site, you will know that the entire construction site would not function without cement, and cement comes from limestone. So obviously sedimentary rocks are extremely important in that respect, because the entire building industry would pretty much fall to pieces if we didn't have access to limestone to make cement. And then there are other types of rock which are useful to us, things like the evaporites. Those are rocks which are produced by the evaporation of water. So as the water evaporates away, it has to leave behind the minerals, well, the minerals that were dissolved inside the rock. Those minerals can't go with the water as it goes into the atmosphere, so they have to get left behind. So a classic example of that would be something like if you have a glass of water and you dissolve some salt in it, then you leave that glass of water on the windowsill for several days. The water's going to evaporate away, but the salt gets left behind. And imagine doing that on a large scale. Imagine taking a body of water, something the size of the Mediterranean Sea, for instance, and just letting that entire body of water evaporate away, while all of that salt and all the calcium sulfate and other bits that are within that water dissolved in it will be left behind, and they'll form a big thick layer of material at the bottom, which we refer to as evaporites. So why do we want to study sedimentary rocks? Well, one of the key things in geology is, of course, the principle of uniformitarianism, and that says the present is the key to the past. I do apologise for getting confused there. It essentially means that what we can see today also happened in the past. So if we can come up with a set of criteria to describe something, we can look for those criteria in rocks from the past, and we can say, right, this is what was going on. So for instance, if I go out into a desert now and I look at the sand that's being blown about in a desert, well, I can look at that sand. I can say, how big are the pieces of mineral that make up this sand? What minerals are in this sand? How rounded are they? How well sorted are they? You know, what color does this sand have? What other minerals are in there? What sedimentary structures are forming? Well, I can see ripples and dunes, and they're going to leave indications in this layer of sediment as well that they existed. And so what I can do is I can take all this information together, and I can take this information and say, right, these are the criteria for a modern desert environment. And then what I'm going to do is I'm going to go to a layer of sandstone. And I'm going to look and I'm going to say to myself, can I see these same things? Can I see the same types of minerals? Can I see the same kind of like sizes of minerals? Can I see, were the class the same roundness? Are the class the same, are they well sorted or are they poorly sorted? Are they the same structures? And based on that, I can say, right, well, this layer of sandstone did or didn't form in a desert. If it shows the same features, then yes, it probably formed in a desert. If it doesn't show those features, it probably didn't form in a desert. So we can use the present day to tell us about rock layers, but we can also use rock layers to tell us about what happened in the past. So things like, for instance, predicting volcanic eruptions and to some degree trying to predict earthquakes can be essentially helped by looking at the rock record. Obviously, sedimentary rocks tell us about past environments. So as a sedimentary geologist, one of the things you're going to try and do is if you walk up to a layer of rock, you're going to try and work out in what type of environment did that layer of rock form. A desert, a glacier, a beach, the deep marine, and that's going to tell you about the environment. And so what you can see in this picture here is you can see we have a sequence of sedimentary rocks coming from the rocks down here at the bottom, which are probably the oldest, to the rocks up here at the top, which are probably the youngest. And so as we go up from one layer to another, to another, to another, the environment could be changing. And so what we're getting essentially in this picture is if we were standing right here at the bottom and we worked out the environment in which each layer of rock formed, essentially we have a timeline, don't we, telling us, right, in the Cambrian we're in this environment, in the Ordovician we're in this environment, in the Silurian this environment, Devonian this environment, etc. So essentially we have ourselves a timeline, and it tells us these were the conditions throughout geologic time at this location where I am standing. So sedimentary rocks also tell us about past climates. So they give us very strong indicators of what the conditions in that area were like, but also they give us good indications of what the global conditions were like. So that's one of the things that we use when we start talking about things like global warming. And okay, when it comes to global warming, you can say, right, well, how do these geologists, how do these scientists know that the Earth is getting hotter? Well, a lot of the written records that we have will only go back a few hundred years. And so you can say to yourself, right, well, this is only a very, very small portion of geologic time. So, when it really comes down to this, what kind of, is this good enough evidence to say that the world is getting hotter? What geologists can do is we can look at sedimentary rocks and we can look at sediments and we can look at the evidence within those rocks and we can say, right, this kind of range of temperatures, this is the kind of range of temperatures in which this particular rock formed. This is telling us something about what the conditions were like in this area at this point in time. And so what we can see as a geologist is we can see the fluctuations in global temperature throughout geologic time. And we can say, right, well, this is the kind of rate at which we would expect to see global temperatures changing. And one of the things that we see as geologists now is we see that the rate at which global temperature change is occurring is considerably faster than in most other instances in the geologic past. So something a bit weird is going on. And when you really start crunching the numbers and trying to work out, well, what's the thing that could be causing this weird event, the obvious answer is it's us. It's humans. Sedimentary rocks also tell us about past events. So they're going to tell us about things like landslides. They're going to tell us about periods of time where we have periods of uplift, where rocks are being pushed upwards. They're going to tell us about periods of time where we have essentially the sea levels rising and water moving onto the continents. And once again, that's a direct reflection of global climate in most instances. So that's going to tie back into past climate. As we've already gone and discussed, the layers of sedimentary rock that we have in a sequence essentially give us an ordered sequence of events. If you start down here, once again, principle of superposition, oldest rocks at the bottom, youngest rocks at the top. You can come up with a sequence of events starting with, right, once I know what environment this rock formed in, then this rock, then that rock, then that rock, that rock, that rock, that rock, that rock, and so on up through the sequence. And essentially you are producing a sequence through geologic time, a slice through geologic time, in which you are working out what was happening in this area essentially throughout whatever portion of geologic time this cliff face here represents. And then obviously sedimentary rocks are the only type of rock that give us a clue when it comes to ancient life. So after about 541 million years ago, we start having life that has hard bodies, and so we begin to see those hard-bodied fossils occurring, well, animals occurring as fossils in the rock record. Now, in some cases, soft-bodied organisms, which are older than 541 million years, are also preserved, but they are far, far rarer. All right, so that's the end of part 1. Please take a break, have a walk around, and we'll start part 2 shortly.